above the resonance, the phase shift is pi, and you see this change in sign in the signal. Now, when we do the same experiment with a bilayer sample, we see something more complicated. So here is gold and permalloy, and here is palladium and permalloy. And so here you see the voltage as a function of field, and the black data points are the actual measured data. Now you still see something that's first negative becomes positive, but it's not purely anti-symmetric in the resonance fields like this magnetoresistive signal. There's an additional symmetric contribution. So what you have is you have two contributions. One is due to the magnetoresistance, and the other one is due to spin Hall effects. And so the blue one is the spin Hall effect contribution, the green one the magnetoresistance. And if you add the two together, you get the red curve, which is the fit to the data. So the spin Hall voltage we can express by this equation. Again, don't worry about the details. What is important is it's directly proportional to the spin Hall angle. So the magnitude of this blue signal tells you immediately what the spin Hall angle is. And it's also proportional to the length of the device. So if the spin Hall angle is very small, we only have to make our device longer to get a bigger signal. And the signal here that we get is pretty nice. I mean, it's a couple tens of microvolts, so it's very easy to measure. So, and if we get spin Hall angles for gold that are 0.3%, so it's smaller than the limit that we measured in our earlier measurement, so that's good. For palladium, it's a little bigger. It's about 0.8%. So what we can do is we can do these experiments for many different materials. You know, it's very easy to integrate these bilayers with these coplanar waveguides. So we've done this for platinum, palladium, gold, moly, also some for bismuth. And so what we see, spin Hall angles for platinum are the biggest, 1.3%, and that's pretty much consistent with what other people see. Palladium, it's around 0.8%. Gold, it's 0.4%. Bismuth is similar to these two, about 0.9%. Molybdenum is negative and much smaller, minus 0.25%. But so now what we can also do is we can compare these results to theoretical calculations of spin Hall conductivity. There's this guy, Gu Yonggu at National Taiwan University, who calculates these spin Hall conductivities using first principle calculations. And he did this for palladium, platinum, and gold. And what is interesting is he calculated his results a year or two before we published our experimental results. And when we did our experiments, we were totally unaware that he had actually published these papers. So this was like a double-blind experiment. But what is